In the setup function, I set my serial port speed and set the analog pins as inputs. In the loop, I used analog read to read the value of the potentiometer from A2, which I defined as pot. I also used analog read to read the value of the end scope from A1, which I called end scope. I defined the variable Fs, which is the sampling frequency, and set that to pot so that way I could adjust the potentiometer to the appropriate sampling frequency. I then found delta t, which was plugged into the delay function. In the end scope, I turned on the A1 and was able to change the frequency with respect to the frequency values given to us, which were 75, 100, 215, and 300 Hz. Then, once I ran the processing code and told it what port to read, I used the potentiometer to try and get the sample rate as close to the given sampling frequencies, which were 500, 200, 142, and 100 Hz. Here's the setup of my end scope in Arduino. In the end scope, I set the frequency to 75 Hz. Then, using the potentiometer, I was able to set the sampling frequencies. In the 500 Hz sampling frequency, you can see here that there's no aliasing as that peak is right around 75 Hz. The same can be said for the 200 Hz sampling frequency. We see that the peak is at around 75 Hz as well. For the 142 Hz sampling frequency, we do see aliasing as that peak is around 67 Hz. Similarly, the 100 Hz sampling frequency has aliasing as well, and that peak is around 21 Hz. Now I set the frequency to 100 Hz in the end scope. For the 500 Hz sampling frequency, you can see that there's no aliasing as the peak is right around 100 Hz. The same can be said for the 200 Hz sampling frequency. We see that peak around 100 Hz as well. For the 142 Hz sampling frequency, we do see aliasing as the peak is around 42 Hz. Similarly, the 100 Hz sampling frequency has aliasing as well, and that peak is around 1 Hz. I set the frequency to 215 Hz in the end scope. For the 500 Hz sampling frequency, there is no aliasing as that peak is right around 215 Hz. The 200 Hz sampling frequency does have aliasing as the peak is around 17 Hz. For the 142 Hz sampling frequency, we also see aliasing as the peak is around 67 Hz. And lastly, for the 100 Hz sampling frequency, it also has aliasing and the peak is around 11 Hz. I set the frequency to 300 Hz in the end scope. For the 500 Hz sampling frequency, there is aliasing as that peak is right around 200 Hz. The 200 Hz sampling frequency has aliasing as the peak is around 93 Hz. For the 142 Hz sampling frequency, there is aliasing as the peak is around 16 Hz. And lastly, the 100 Hz sampling frequency has aliasing as well as that peak is about 3 Hz. For the 75 Hz signal frequency, the 500 Hz and 200 Hz sampling frequencies did not alias, but the 142 and 100 Hz sampling frequencies had aliasing. For the signal frequency of 100 Hz, I found that the sample frequencies of 500 and 200 did not alias, but the 142 and 100 frequencies did. For the 215 signal frequency, only the 500 Hz sampling frequency did not alias. All the rest did. For the 300 Hz signal frequency, all of the sampling frequencies aliased. In this chart, you can see the Nyquist frequency, which is half the actual value, the Nyquist rate, which is 2 times the signal frequency, and then you can see the theoretical alias frequency versus the experimental alias frequency. It's important to note that when the sampling rate frequency is greater than the Nyquist rate, there is no aliasing observed. Here's the square wave. You can see a peak about every 10 Hz, and that's because to make a square wave, you need an infinite number of sines and cosines at different frequencies and amplitudes. And on the end scope, I changed from analog output to pulse output by turning off A1 and turning on P1. And my circuit changed because I removed the wires from A1 and put them in P1. A triangle wave is similar to a square wave, except it takes in a smaller number of sines and cosines, so there are fewer peaks. As you can see here, there are about only 1, 2, 3, 4, maybe 5 peaks. And here's my circuit.